What if I told you that a massive 30-year medical study tracking nearly 90,000 women revealed that regular mammograms didn't actually save any more lives than just a standard non-mammogram physical exam?
I mean, it's a completely staggering claim, right?
It really is. And the question is, how do we take a claim that controversial, that emotionally charged, and mathematically prove whether it's true or just, a statistical fluke?
Yeah, because we are constantly bombarded by claims like this every single day.
Exactly. You see a headline about a medical breakthrough or some poll claiming 90% of voters are outraged about something, and there's this immediate reflex to either panic or celebrate. We tend to treat statistics like they're a high-definition photograph of the truth.
Right, but the problem arises when you look closer and realize that photograph is actually a painting,
Yeah.
and maybe the painter was wearing a blindfold.
Wow. Yeah.
It's the ultimate modern dilemma. How do you separate the signal from the noise? How do you know when a number is a genuine reflection of reality and when it's just, well, a statistical mirage?
Yeah. And that is exactly the mission for today's deep dive. We are taking the dense, highly mathematical world of statistical inference, specifically Chapter 6 from the Open Intro textbook, and we're translating it into a practical toolkit.
A toolkit that everyone really needs right now.
For sure. For you, the listener, this is about upgrading your mental software. You're constantly subjected to poll results, medical study claims, demographic data, all of it. Today, we are going to build the mathematical BS detector that statisticians use to separate random chance from undeniable facts.
And we could do it without the dense jargon.
Right, no jargon. We're focusing on the real-world aha moments hiding inside these equations.
Because the math we're exploring, it really isn't just numbers on a page. It's a highly structured way of arguing with reality. It forces us to ask what we actually know versus what we simply assume.
Okay, let's unpack this. Before we can understand complex scientific claims, we have to understand how statisticians measure just one thing accurately. So we begin by looking at estimating a single proportion.
Right, the foundation.
Yeah. There's a study in our sources about payday loan borrowers. A simple random sample of 826 borrowers was surveyed, and the researchers found that 70% of those respondents supported new regulations on payday lenders.
Which sounds incredibly straightforward.
It does. But to trust that 70% number, the text says statisticians use something called the success failure condition.
Yeah, so to safely assume that your sample actually represents the whole population, you want to be able to model your data using a normal distribution.
The famous bell curve.
Exactly, the predictable bell curve. But you can only use that bell curve if you have enough data. Specifically, you expect to see at least 10 successes and 10 failures in your sample.
I used to find that rule incredibly arbitrary until I started thinking about it like baking a cake.
Oh, baking a cake.
Yeah, think about it. The normal distribution is the final, perfectly baked cake. But the success failure condition, that's your minimum ingredient requirement. You need at least 10 successes and 10 failures, like needing flour and eggs, to make the recipe work at all.
I actually love that analogy.
Right. If you survey a small group of people and only get, say, 3 successes, well, you don't have enough flour. The recipe completely collapses. You don't get the bell curve. It just falls flat no matter how good your math is. Once you hit 10 successes and 10 failures, you finally have the basic fundamental ingredients for the normal curve to actually rise.
That makes perfect sense. The mechanism there is predictability. The normal distribution is the holy grail for statisticians because it behaves according to very strict mathematically proven rules.
So it takes the guesswork out.
Precisely. It allows us to calculate the standard error. And the standard error is essentially the average distance we expect our sample's estimate to be off from the true reality of the entire population.
But without the flour and eggs, without the 10 successes and failures, you can't calculate that.
Exactly. If you lack those fundamental ingredients, the curve becomes skewed. You lose that predictability, the standard error becomes meaningless, and any conclusions you draw are going to be fundamentally flawed.
Okay, so in the payday loan study, with 826 people and a 70% support rate, they had about 578 successes and 248 failures. Plenty of ingredients.
Very well-baked cake.
Exactly. So they can confidently calculate their standard error, and from that, their margin of error. But reading through this raised a major question for me.
What's that?
If I'm a pollster and I want to run a brand new poll with a margin of error of exactly 4%, how do I know how many people to survey in the first place? Do I just, look at historical data to guess what the outcome will be?
That is a common assumption, but mathematically, it's actually a trap.
Really? Why?
Because if you rely on past data and the public's opinion has shifted drastically since then, your sample size will be completely wrong. Our sources outlined a brilliant mathematical trick for this.
Oh, right, the P$5 thing.
Yes. When you're designing a poll and calculating how many people you need to hit a specific margin of error, you assume the final outcome will be exactly a 50-50 split. You literally plug P$0.55 into the equation.
Wait, why 50-50? What if I'm polling something obvious like, whether people like sunshine?
Well, if you think about probability, a 50-50 split represents maximum chaos.
Maximum chaos. I like that.
It is the absolute worst-case scenario for a statistician. Think of a coin toss. If a coin is weighted to land on heads 90% of the time, it's highly predictable. You don't need to flip it very many times to figure out what's going on.
Because it just keeps coming up heads.
Right. The margin of error naturally shrinks because the outcome is so consistent. But if it's a perfectly fair coin, landing heads 50% of the time, the uncertainty peaks. The variability is at its absolute maximum.
So by assuming 50-50, they're forcing the math to calculate the largest possible margin of error.
It's a purely defensive strategy. They assume the highest level of uncertainty to ensure they survey enough people to cover themselves.
So they don't get caught off guard.
Exactly. If the real-world result ends up being, say, 70-30, their margin of error will actually be smaller and more accurate than they promised.
Okay, that is fascinating. So for you listening, the next time you see a political poll on the news claiming a 4% margin of error, you'll know exactly the worst-case scenario math they used behind the scenes to arrive at the number of people they surveyed.
And usually for a 4% margin, that 50-50 assumption dictates you need around 600 people.
It's like packing for a trip and assuming it's going to rain every single day. If it's sunny, great, you over-prepared. But you're protected against the worst.
That's a great way to put it.
So measuring one group like that is the foundation. But human curiosity never stops at just one group. Once we can confidently measure group A, we immediately want to know, is it better than group B?
Right. Does this thing actually work?
Exactly. We transition from the abstract math of polls to the high-stakes world of medical trials. This is where statistics shifts from merely observing the world to actively testing how the world works.
Because when we compare two proportions, we are looking for a difference. Does an intervention actually save lives, or is any difference we see just a phantom of random chance?
Which brings us back to that massive, incredibly sobering breast cancer study from our sources.
Yes, the 30-year study.
Nearly 90,000 women were involved. During a 5-year screening period, these women were randomly divided into two groups. Half received regular mammograms, and the other half received regular non-mammogram breast exams.
And then they tracked the death rates from breast cancer over the next 25 years.
Right. And the results they published are just startling. Out of roughly 45,000 women in the mammogram group, 500 died of breast cancer. Out of the 45,000 in the control group, 505 died.
A tiny difference.
The death rate was basically identical.
Right.
Mathematically, the researchers concluded there was no statistically significant difference between the two groups.
With 90,000 participants over 3 decades, the statistical power of this study is immense. It really forces the medical community to look at the collateral costs of an intervention.
What do you mean by a collateral costs?
Well, if mammograms do not offer a clear survival benefit over regular exams, we have to look at the physical and emotional harm of the procedure itself. The study's authors point out a major issue, which is overdiagnosis.
Right, overdiagnosis. So finding cancers that technically exist but would never actually cause symptoms or threaten the patient's life before they died of something else.
Yes.
But because the screening finds it, it gets treated with surgery, radiation.
Causing immense trauma for a problem that was never going to materialize in the first place. Statistical inference isn't just an academic exercise. It dictates public health policy and directly impacts human well-being.
Here's where it gets really interesting, though. I push back on the text here.
Oh.
Yeah, when the statisticians check their conditions for this mammogram study to see if they have enough ingredients to bake that bell curve cake, they use something that feels totally backwards.
You're talking about the pooled proportion.
Yes. They calculate this pooled proportion. They take all the deaths from both groups, add them together, and divide by the 90,000 total women to find a single combined death rate. Wait, if we are actively trying to prove that the mammogram group and the control group are different, why on earth would we pool their data together to check our conditions? Isn't that defeating the whole purpose of a comparison?
What's fascinating here is that this gets to the very core of the scientific method. It all comes back to the null hypothesis.
The null hypothesis.
Yes. In science, the burden of proof is always on the intervention. You must assume that the intervention, in this case the mammogram, does absolutely nothing until you have overwhelming mathematical evidence to the contrary. The null hypothesis literally states that the two groups are mathematically identical.
Innocent until proven guilty.
Precisely. Identical until proven different. So if we are forcing ourselves to assume they're identical, we are mathematically required to pool their data together to find the truest, most robust baseline rate of breast cancer deaths. We use that pooled rate to check our success-failure conditions and calculate our standard error. We only abandon that pooled assumption if the final evidence is so overwhelming that it forces us to abandon it.
Like the p-value.
Exactly, the p-value.
I see p-value thrown around in science news all the time, but nobody ever actually defines it. For someone trying to upgrade their mental software today, what actually is a p-value?
A p-value is simply a probability. Specifically, it's the probability of observing the data you just collected, or something even more extreme, if the null hypothesis is perfectly true.
Give me an example.
Let's say your p-value is 0.04. That means if the intervention actually does nothing, there is only a 4% chance you would see these results purely by random luck.
That's super low.
Right. Because 4% is so remarkably low, you reject the idea that it was luck, and you conclude the intervention actually worked. But in a mammogram study, the p-value was very high.
Meaning the tiny difference between 500 deaths and 505 deaths could very easily happen by pure random chance.
Yeah.
Okay, that makes perfect sense. A low p-value means the results are too weird to be an accident. But the sources provide a really cool contrast to this with a corporate example.
The drone parts.
Yeah, the Phantom quadcopter drone. A company is testing new rotor blades from a prospective supplier, but the new blades are more expensive, so the company doesn't just want to know if they're slightly different. The company explicitly claims the new blades are 3% better.
A very specific claim.
Right. So if I'm setting up this math, do I just pool the data again because of the null hypothesis?
But not this time. In the drone scenario, the null hypothesis is not 0. The null hypothesis is that the difference is exactly 3%.
Oh.
Because we are not assuming the two groups of blades are identical, we do not pool the data. We keep the groups separate when checking our conditions. The formula actually subtracts that 0.03 from the observed difference before dividing by the standard error.
It's a subtle shift, but it shows how the mathematical tools adapt to the specific real-world question being asked.
It's very elegant.
It is. We've scaled up from a single poll to a massive medical showdown and even into corporate supply chains. But society is rarely a simple binary, right? We don't just exist in two groups.
No, reality is much messier.
What happens when a hospital wants to compare survival rates across 5 different departments? The two-group math breaks down. We need a new tool. Which brings us to the final level of our deep dive, the chi-square test.
The chi-square test.
How do we mathematically prove if a system with multiple overlapping categories is fair or biased?
This is the realm of goodness of fit. We have an observed reality across multiple categories, and we have an expected baseline reality, and we need to mathematically prove if they fit together nicely or if the system is rigged.
The sources give us a fascinating example, jury selection. Imagine a small county with 275 jurors. The demographic breakdown of the entire registered voting population is 72% white, 7% black, 12% Hispanic, and 9% other.
Okay.
If the system is perfectly fair and jurors are chosen purely at random, that 275-person jury pool should reflect those exact percentages.
And we can calculate those expected counts easily. 72% of 275 is 198. We would expect 198 white jurors. We expect about 19 black jurors, 33 Hispanic jurors, and roughly 25 from other races.
But reality is messy. The actual observed counts on the juries were 205 white, 26 black, 25 Hispanic, and 19 other. It doesn't match perfectly.
It rarely does.
But is it just random chance, the luck of the draw, or is there systemic bias in how jurors are being selected? My analogy for this is a wobbly car tire.
A wobbly tire.
Yeah. If you look at a tire and see a single scuff mark or a tiny deviation on one side, it might not mean much. It's just random wear and tear. But if you measure the wobble across 4 or 5 different points around the rim and you add all those wobbles together, you can prove mathematically that the entire tire is fundamentally unbalanced and needs to be replaced.
I love that analogy. It captures the concept so well. But it does miss one mathematical reality, which is that some wobbles matter significantly more than others.
Okay, how so?
To solve this, we can't just add up the raw differences. We have to evaluate the entire system simultaneously using the chi-square test statistic. To calculate it, we look at each category. We take the observed count, subtract the expected count, and then we square that difference.
Wait, why square the difference? Why not just add them up? If I have 7 extra white jurors and 8 fewer Hispanic jurors, why do I need to square the numbers?
Two crucial reasons. First, if you just added the raw differences, the positive deviations and negative deviations would cancel each other out.
Oh, right.
A +7 and a -8 would leave you with a total wobble of -1, making the system look almost perfectly fair when it isn't at all. Squaring any number, positive or negative, makes a positive. It captures the absolute size of the wobble no matter which direction it leans.
That's brilliant.
And the second reason is that squaring massively exaggerates unusually large deviations. If a difference is small, say 2, squaring it makes it 4. But if a difference is unusually large, say 10, squaring it turns it into 100. It shines a massive mathematical spotlight on statistical foul play.
Wow, okay, but wait, I'm looking at the formula here in the text. It says you square the difference, and then you divide by the expected count. Why divide? If we already squared it to magnify the big errors, why add another step?
Context and proportionality. Being off by 5 jurors matters a ton if you only expected 10 jurors in the first place. That is a massive deviation.
Half the group.
Exactly. But if you expected 10,000 jurors, being off by 5 is meaningless statistical noise. Dividing by the expected count scales the wobble to the size of the tire, to use your analogy. It ensures we don't accidentally flag a massive category as biased just because it has a high raw number of minor deviations.
Okay, so we find the squared difference for the white, black, Hispanic, and other categories, divide each by their expected counts, and add all 4 results together. That gives us our final chi-square number, our total sum of the wobble.
Precisely.
But the text says we have to map that number onto a probability curve using degrees of freedom. What does that actually mean?
Degrees of freedom essentially accounts for how many categories you're checking. Think about it. A tire with 4 points of measurement has a different baseline expectation of natural wobble than a tire measured at 20 points.
Because there's more opportunity to find a wobble.
Yes, the more categories you measure, the more natural variance you expect to find simply by chance. The degrees of freedom, which is usually the number of categories minus 1, reshapes the probability curve. It makes sure the test remains accurate and doesn't generate false alarms regardless of how incredibly complex the system gets.
This is your ultimate BS detector. It's how watchdogs can look at a company's hiring practices or a county's jury pool and mathematically prove whether random chance is actually masking a broken, biased system.
Exactly. If we connect this to the bigger picture, what we've walked through today is really an escalation of rigor.
Yeah, it is.
We started with the basic assumption of maximum uncertainty in a single poll. Then we moved to the extreme skepticism of the null hypothesis in medical trials, and finally arrived at the systemic stress test of the chi-square formula.
So what does this all mean? We started with a blurry photograph of the news, and we've given you the lenses to snap it into focus. From the baking ingredients of the normal curve to the wobbly tire of systemic bias, statistical inference isn't just a textbook chapter. It's the language we use to decode reality.
It is the language of truth.
Yeah.
But, I want to leave you with a thought that brings the math out of the textbook and into your personal life.
Okay.
Today we talked about the mathematical trick of setting p$0.55 in polling, assuming the absolute worst-case scenario of maximum chaos, just so the pollsters could feel safe with their sample size.
Right.
And we also talked about the tragic overdiagnosis in the mammogram study, finding remote problems that were never going to hurt the patient, but treating them anyway, causing immense unnecessary harm.
Those are 2 very heavy concepts to put together.
They are. And this raises an important question for you to reflect on. How much time, energy, and emotional bandwidth do you spend treating the worst-case scenario as a given, just to feel safe? And like the patients who suffered unnecessary treatments from overdiagnosis, are the protective measures you are taking in your own life actually causing more harm than the remote problems you were trying to prevent?
Wow. Wait, really? Are you overdiagnosing your own life? That is going to stick with me. Remember, you don't have to react to the blurry picture right away. You have the BS detector now. Look for the baseline, check the wobble, and don't let the noise convince you the sky is falling.